The next speaker is Andrea Bianco from Powertech Engineering. The title of the presentation is Piston Cooling Jets for High Performance Engines, Development of a Simulation Strategy based on Moving Particle Simulation and Conjugate Transfer. Andrea Bianco is responsible for 3D simulation, 3D CFD simulation projects and R&D activities at Powertech Engineering. He has a background and a master degree in automotive engineering from the Polytechnic of Torino in 2007, and he has worked as a researcher in the engine field for Fiat Research Center, Politecnico di Torino, and Johnson Electric prior to joining Powertech Engineering in 2015. He has quite a wide experience in 3D simulation, CFD simulation, covering several topics from combustion to pollutants, after treatment system, multi-phase simulation, air acoustic and thermal analysis of internal combustion engine, electric vehicles, and batteries. And Andrea has authored and co-authored more than 20 papers and conference presentations in the field of powertrain, numerical simulation, and also related to experimental testing. Andrea, please.
Okay, so thanks a lot for your kind introduction, and good day, everyone. Today I'm here to talk about the piston cooling jets for high-performance engines, in particular on the development of a simulation strategy based on moving particle and conjugated transfer simulations. I would like to mention that this work is the result of collaboration between Powertech Engineering and the Politecnico di Torino, and I'd like to acknowledge the contribution of my co-authors, Mattia Prestifilippo and Professor Federico Millo. Let me just also introduce in one slide our company. Powertech Engineering is a consulting firm based in Turin, employing 40 engineers, and our core business is to provide simulation services mainly to the automotive field. We are specialized in powertrain and vehicle simulations, ranging from 1D to 3D CFD, but we are very active also in hardware in the loop and software in the loop applications with our own test benches. We work mainly for the transportation sector for both on-highway and off-highway applications, but we are very active also in marine sector and the power generation sector. So, coming to the agenda for today, we will start with an introduction, and then we will describe the methodology we have followed and the main results we have achieved for selected case studies, and then we will wrap up the main outcomes in the conclusion. So, first of all, what the piston cooling jet is? Well, I think that given the presentation we have seen this morning, I can go rapidly through these slides. I would just like to mention that basically, thanks to the fact that we are able to control piston temperature, we are able to reduce knock tendency and increase power density and power output of the engine. Unfortunately, it is quite difficult to characterize this kind of system from the experimental point of view, and therefore we have really to rely on simulations in order to overcome the lack of experimental data, as well as to support engine development and perform also optimization studies. So, this is the typical workflow that we previously adopted in Powertech to tackle this kind of simulation. So, starting from a piston design, we performed a 3D CFD piston cooling jet simulations using infinite volume-based software, and then we performed a CHT analysis in order to extract the piston temperature distribution, as highlighted by this figure on the right. Unfortunately, finite volume-based simulations are quite complex because we have to deal with moving meshes, and this increases the user effort. And additionally, we have to deal with several multi-phase models, such as VOS, for example, for the jet coming out of the nozzle. Then we have Lagrangian models for the droplets, and eventually liquid film models for the liquid film forming downstream of the impingement zone. So in this scenario, we asked ourselves if it was possible to leverage the advantages given by Particleworks in order to speed up these kind of simulations and integrate them within our conjugated transfer workflow. So basically, in other words, we wanted to move from the upper arrow to the lower arrow, where we substitute finite volume-based simulation with Particleworks, having the advantage of having a meshless approach, and where we basically use a particle-based description of the whole liquid. And this translates in reduced lead time, and for us also the possibility to perform optimization studies. In order to do so, we use what we call the stair-step approach. So at each step of this stair, we focused ourselves on a modeling of a simple problem still related to piston cooling jets. And then we'll move on to the next step, leveraging the knowledge gathered in the previous one. So, for example, we started with simple flows, and we focus on what happens within the nozzle, for example. Then we studied impinging jets in order to characterize the transfer coefficient in the impingement zone and downstream of it. And then we moved on with the piston cooling jet studies, starting from simplified simulations up to the full integration with conjugating transfer studies. For the sake of brevity, in this presentation, we will focus only on impinging jets and full piston cooling jet simulations with conjugated transfer. So starting from impinging jets, in this case, our objective was the identification of a simulation setup able to correctly predict heat transfer coefficient in the impingement point and downstream of the impingement zone. And in order to validate this simulation setup, we performed an extensive literature research by means of which we identified the suitable experimental data. And we found out also that post-impingement dynamics are severely affected by the condition of the flow exiting from the nozzle. For example, here we have some images showing what happens when we have a laminar flow impacting on a flat plate. And this is very different from what happens when we have a turbulent flow coming out from the nozzle. And even in a turbulent condition, when we increase the Reynolds number, we have post-impingement dynamics which are severely changing. In order to be as representative as possible of engine-like conditions, we selected this experimental data set, which is summarized in this slide, related to a turbulent flow. Basically, we have a nozzle having a diameter of 4.1 millimeter, placed 2.5 diameters away from a flat plate, and then this jet is impinging normally on this flat plate while gravity is acting in the opposite direction. The plot on the right is showing normalized Nusselt coefficient versus normalized distance from the impingement point, and we have black squares for experimental data, while the black line is showing a correlation proposed by the authors of the experimental research focused on what happens near the impingement zone. So here, for example, 2.5 diameters away from the impingement point, we have a transition to a fully turbulent condition, and that's why we have these heat transfer coefficients higher than the correlation proposed by the authors. In order to simulate these conditions in Particleworks, we used the setup which is summarized in this slide. And among these settings, I would like to underline that we have used an uniform velocity distribution at the exit of the nozzle, and that we have basically simulated 0.2 seconds with a maximum current number of 0.2, and that we have performed a particle size sensitivity study. As far as the transfer coefficients are concerned, the underlying assumption in Particleworks when we use the Nusselt correlations are that we are simulating a steady flow on a planar surface with a developing boundary layer. And therefore, these are the correlations which are normally used in Particleworks. In our case, since we are modeling an impinging jet impinging normally on a flat surface, we have modified these correlations using literature data in order to be the one shown here at the bottom and already take into account the direction of the flow. Here we have some highlights of the results we have achieved. So, for example, on the left, we have the heat transfer coefficient on the flow developing on the flat plate, while on the right, we have time average each heat transfer coefficient measured at the end of our simulation. And you can already see a qualitative agreement with experimental data because we have a decrease in heat transfer coefficient when we move along the radius. Looking at the quantitative data, here we have the same plot we introduced before with the addition of three curves for numerical results. So we have in light blue particle results for 0.5 millimeter, then in yellow particle size 0.3 millimeter, and in green the particle size 0.1 millimeter. Generally speaking, I would say that we see slight variation depending on particle size, and in all the cases, numerical results are all able to correctly catch the transition to fully turbulent conditions starting from 2.5 diameters downstream of the impingement point. And in addition, all numerical results are in very good agreement with experimental data already starting 1.5 diameters downstream of the impingement point for all the particle size above 0.1 millimeters. You can see that there are still some difference in the impingement downstream of the impingement zone below 1.5 diameter and on the impingement point in particular. So having achieved this, we asked if it was possible to further improve results in the impingement zone. And thanks to Prometech support, we ended up in using this multi-zone HTC script, in which basically we subdivide the post-impingement zone in several subzones, in each of which we use a different heat transfer coefficient correlation. And these correlations are then updated considering impinging jet velocity, nozzle diameter, fluid dynamic conditions of the liquid, as well as nozzle to plate distance. Using this kind of script, we have obtained the results highlighted in the same plot we've seen before, but in this case with the red curve. And you can see that basically we are still able to correctly obtain very good results when we are far away from the impingement zone. But in this case, we have also significant improvement in the impingement zone and on the impingement point in particular. The only differences still present, basically related to this point at 0.6 diameter downstream of the impingement point, were deemed acceptable, and therefore this precision was sufficient for the purpose of our study. So, coming to piston cooling jets, in this case, we took the opportunity to support the development of a new kind of piston for high-performance engines. In particular, this piston was developed for V-type engines running at more than 9,000 RPM speed. And in this slide, we have also layout of the piston cooling jet configuration that we have considered. Basically, we have a couple of nozzles having diameter below 2 millimeters and a flow rate higher than 6 liters per minute. And you can see that we have this exhaust side nozzle, which is targeting a zone of the piston bottom right below the exhaust valve pockets. While for the intake side oil jet, we have an oblique orientation because we are targeting the achievement of a spread of this oil jet on a wider area of the piston bottom. For the simulation setup, here we have a summary of the settings we have used. Basically, it is a carryover of what we have just seen for the impinging jet cases. I would just like to mention that we have simulated 3 engine cycles. We have neglected particle-air interaction as a first approach. And again, we have performed a new particle size sensitivity study. And basically, we have used, again, the multi-zone HTC script we have just validated before. Here we have a couple of videos showing what happens with the running engine and piston cooling jets active. We have in red the oil jet coming out from the exhaust side nozzle, and in blue the one coming out from the intake side nozzle. And in this case, the complete crank train was included in the simulation. So I swear it is there. You can see it because of confidentiality reason, but you can see, for example, the deflection of the intake side oil jet due to the interaction with the side of the connecting rod. And indeed, it was mandatory for us to include the complete crank train because we were effectively looking for this kind of interaction between the intake side jet and the connecting rod in order to allow a wider area of spreading of the intake side oil jet and in order to reach as much as possible a big portion of the piston bottom. Here we have some other information concerning particle velocities. So we have slower particles in blue and faster particles in red. And basically, you can see that we have the slight different velocities between the intake and the exhaust side particles, especially when we move from piston top to piston bottom. This is more visible if you extract some frame from this video. Here they are. So we have a TDC on the left, half stroke position with descending piston, then BDC position, and half stroke position with ascending piston. So, for example, if we look at BDC, we have comparable particle velocities between intake and exhaust side particles, while on the contrary, if we look at TDC and half stroke position with descending piston, we have very different velocities between the exhaust side and the intake side. This basically happens because the jets exiting from the exhaust side nozzle is directly impacting on the bottom of the piston, while the jet exiting from the intake plate interacts with the connecting rod side and then only afterwards reach the piston bottom. And so it has lower velocities. If you focus on the first part of the engine cycle, here we have the piston moving from TDC towards BDC. We can see that these kind of interactions already start at the TDC position and last until we reach the upstroke position, but the deflected droplets reach a different part of the piston bottom. So we are, as shown by these arrows, basically. And this means that we are effectively spreading the oil jet towards different sides of the piston bottom during the engine cycle. If we focus on the second part of the engine cycle, so when the piston is moving from BDC to TDC, we can see a peculiar phenomena happening at upstroke position, because if we look here, you can see that the oil jet is following the side of the connecting rod. So thanks basically to a Coanda effect, we are able to let this oil jet go around the little end of the connecting rod and reach the zone of the piston bottom, which were not accessible normally. So we are basically overcoming the masking due to the presence of the piston pin. And this is allow us basically to increase further the cooling also in that zone of the piston. Talking about heat transfer coefficients, here we have 4 images showing heat transfer coefficient distribution for different positions of the piston. And focusing on the exhaust side, basically you have this red circle which is moving along the cycle, and this is the impingement zone of the jet exiting from the exhaust side nozzle. It is moving because of the inclination between the exhaust side nozzle and the cylinder axis, basically. On the intake side, instead, we have this red circle visible only here at BDC position, because it is the only position in which we have direct impingement of the intake side oil jet with the piston, basically. Otherwise, we have interaction with the connecting rod, which is spreading the oil jet on a wider area. And these are the reason why we have this kind of green clouds around these images, showing the impact of on a high number of particles having lower velocities. If we extract cycle average heat transfer coefficient, we have the figure on the right, where we have this stretched red zone, which is the trace of the direct impingement point due to the exhaust side nozzle. While for the rest of the piston, you can see that we have a kind of uniform green colored area, which is the trace of the spreading of the oil jet coming from the intake side nozzle. The plot on the left is showing area average heat transfer coefficient along the engine cycle, and we can see here that basically from the second cycle to the third, we have the negligible variation of heat transfer coefficient. So in our case, the simulation of 3 engine cycles was more than sufficient to achieve steady cycle average values. In addition, this kind of fluctuation we see here are consistent with the comments we already did just a few minutes ago concerning the variation of relative velocities of the particles. Here we have also some results concerning the particle size sensitivity study we have performed. So starting from the left for the sample, we can look at these orange bars, which are showing the area average heat transfer coefficient, which is increasing when we decrease the particle size. If we extract area average heat transfer coefficient only from wetted surfaces, we have these blue bars, which instead are showing constant values, basically. So what's happening here is that when we decrease the particle size, it is the wetted surface area which is increasing, and shown by these gray bars. And this basically tells us that the particles in the main impingement zones are doing the same things. It is the sides on which the liquid film develops, which are extending, given to lower particle sizes. The plot on the right instead is showing work clock time, basically as a function of particle size. And here we have that if we move from 0.2 to 0.50 millimeters particle size, we have a slowdown of basically a factor of 5 concerning work clock time. This was, however, acceptable in our opinion, because these simulations are very fast compared to conventional finite volume-based simulations. So we were able to simulate the 3 engine cycles in just 1 day using conventional CPU cores, not GPU, and using a particle size of 0.50 millimeters. And we chosen this size because of the additional, let's say, precision on the wetted area extension. So coming to, there is maybe a misalignment of the slides. I see that it is going forward there, but not here. I'll try again. No? Well, okay. Let's see. Suspense. Well, in any case, I can anticipate the next slide. Basically, we were integrating the results, from Particleworks in our CHT workflow. So basically, the objective here is to compute a cycle average piston temperature distribution. And what we do is to use a model in which we account for the information concerning heat flux coming from from the oil jet. It is not working anymore, so probably it's better if you look, okay. But basically, we are integrating information concerning the heat flux coming from the Particleworks with the information coming from other sources of heat flux. So we have the combustion, the heat transfer with the liner, the friction, and the heat conduction with the piston pin. All these kind of informations, fortunately, it's not working here. It's only working there. So yeah, thanks for turning back. And basically, yeah, sorry. Basically, this allow us to compute piston temperature distribution. And our methodology basically rely on a network of thermal resistances, which is used to account for the fact that each part of the piston is seeing different heat transfer paths around it, depending on what is in contact with the piston. So, for example, we have a path following the rings, a path following the liner, a path following everything is around the piston. The results of this computation are shown here. Okay, if you want, we have also back in the front. We have a piston temperature distribution with the low temperature in blue and higher temperature in red. And we can see some peculiar aspect due to the presence of the piston cooling jet system. For example, you can see this cooler spot between exhaust valve pockets, which is in very good agreement with the zone which is directly impacted by the oil jet coming from the exhaust side nozzle. And basically, thanks to this direct impingement here, we are able to reduce this temperature in this zone, which is a critical zone because we are between the exhaust valves, which is one of the hottest parts within the combustion chamber. And in addition, also the maximum temperature zone is split in two, thanks to the fact that we are able to cool down the zone just behind the piston pin, thanks to the spreading of the oil jet achieved on the intake side, from the intake side, the oil jet. So I know I have to ask you to go look back for one more time. As far as temperature is concerned, here we have a plot showing basically average temperature, maximum temperature, and minimum temperature for our new piston in red compared to literature data, which are shown in gray and in black. So I would say that as far as maximum temperature is concerned, we have achieved a very good agreement with the literature data for high-performance engines. And this is one of the key points we were looking for because maximum temperature really affects the knock tendency and hence power output for the engine. And for the average and minimum temperature, I would say that we are in the ballpark of literature data. So coming to the conclusion, in this case, a simulation strategy was developed for piston cooling jets, leveraging the usage of moving particle simulations and conjugated transfer. As far as impinging jets are concerned, Particleworks showed very good results with the comparison of experimental data using the multi-zone HTC script. And additionally, the setup of the simulation was very easy, so it is an additional advantage. For piston cooling jets, again, the setup of the simulations was extremely easy, and the computational time was reduced significantly compared to finite volume-based simulations. And last but not least, in our case, we were able to compute temperature distribution for a new kind of piston, showing temperature well aligned with the literature data. Talking about future works, we are looking forward to perform some experimental validation of these numerical results and maybe some further optimization of this piston cooling jet system. And with this, I would like to thank you all for your attention. And if you have any questions, I would be happy to add further details. Thank you.
So you ran on 32 CPU. So if you ran the same simulation with finite volume CFD, how long would it take?
I would say at least it's a scale up of a factor of between 5 to 10, depending on the level of refinement we would need. So the speed up we have achieved with Particleworks is very fundamental, in my opinion. It's a key point enabling us to perform optimization studies.
Okay. And did you think about changing the geometry or comparing different configurations of the jets or flow rate values? Is it anything that you think you can do?
Exactly. We are looking forward to perform some sensitivity study concerning not only orientation of the jets, because what we have seen is already well aligned to our expectations. Maybe some study on the sensitivity of these heat transfer coefficient to mass flow rates, and also, let's say, possible modification of the bottom of the piston in terms of geometry.
Yes, one of the new features that was shown in the first presentation today, the import of the heat transfer coefficient via CSV file. One of the aims is to be able to input HTC distribution also on the combustion chamber side to take into account the HTC distribution. So this is something that you can also test with the new version of the software.
Exactly, we are looking forward to that.
Okay, if there is no other.
We have seen, many of us attending the CHT workshop yesterday, have seen the multi-zone approach to the nozzle correlation. And I want to ask if I see that you have applied it on the specific case of the impinging jet, but it seems like it's a kind of general and possibly could be like a universal approach, a universal form of the nozzle correlation, even for the flow along the wall. I don't see exactly into the details of the criteria of the zone definitions, but do you see it as a universal version of the nozzle correlation? Could it be?
Thanks for a very interesting question. I would say that basically, in my opinion, this kind of approach can be generalized. In any case, you have an impingement. So in any case, you have really an impinging jet reaching the surface normally and then spreading on that kind of surface. In that case, basically, the multi-zone HTC script accounts for the fact that you start with a normal impinging jet and then slightly move to a parallel flow condition. So within the script, it is already taking into account all the evolution that you typically have in post-impingement dynamics. So I would say that we are going to use this kind of approach. In any case, we have a significant impingement coming not in parallel direction on a surface. So it is possible also, in our opinion, to maybe evolve a little bit more this kind of script in order to account, for example, for an inclined position of the impinging jet. So that basically you can take into account how is impacting the jet in the impingement point, and then afterwards you will always have basically parallel flow. So that the next part of the script will be the same.
Okay, thanks.
You're welcome. Thanks a lot again for accepting us for this presentation.